Hi, everybody. First, thank you, Olia, for organizing this, and thank you all for joining. I know it's a Sunday and probably not our usual day for going to technical talks. I'm Michael Campos. I work at a venture capital fund called Azolla Ventures. Up until about 2 weeks ago, we were called Prime Impact Fund. I'm here in my personal capacity today, not representing the fund, just as a super fan of geothermal. So we'll obviously talk for the next hour and 20 minutes or so about geothermal. I view it as this massive strategic resource for decarbonization. It's this 24/7 source of renewable energy. The technical potential is nearly limitless anywhere on the planet. And we can harness it with many of the same skills that we've built up over decades in the oil and gas industry. It does beg the question of why it is still a tiny fraction as large as the oil and gas industry. And once I came to that question a couple of years ago, I started going down the rabbit hole and figuring out how we might go about changing this. So in this talk, we'll cover some of the basics, a couple of the key technical and economic challenges, and why, in my opinion, there's never been a more exciting time to be a geothermal entrepreneur. Okay, so an overview of what we'll do here. I'll start with a couple words on my own journey and how I came to geothermal and this talk. We'll go through what is geothermal energy and why I bother with it. We'll go through what's hard about it and why, like I said, why it's never been a better time. And then throughout, so we'll leave some time at the end for questions for sure. But throughout, please also jump in whenever. I would love for this to be a discussion. There are no dumb questions, and push back if something is not clear. Okay, so my journey, I'll start from the beginning. My journey started all the way back in Maryland, where I was born and where I grew up. And I had this pretty sort of typical American upbringing. I think back about it as sort of being at the heart of suburban consumerism. I became aware of climate change at some point in like roughly the high school years, but the way people talked about it, it seemed like we'd have to give up a lot of the way we lived in order to do anything meaningful about it. I looked around and didn't see that happening around me. I didn't see any chance of it really happening around me. Like it didn't occur to me why people would do so, other than out of the good of their hearts. And so I put it off to the side for a while. Along the way, I figured out I really liked chemistry. And so I ran with that. I went all the way through a Ph.D. So I spent my fair share of years in the lab. In my PhD, I studied a type of material called quantum dots. That's what's in this flask here in solution. It's a nano material that absorbs and emits lights really strongly. Here is a flask that I made glow bright red. It wasn't until I was deep into chemistry that I realized that technology could maybe allow us to have it both ways when it came to climate change. Eliminate carbon emissions while increasing standards of living around the world. And I was pretty sure we weren't going to give those up if we had to choose between the two. So after finishing my PhD, I next landed at ARPA-E in the Department of Energy, so back to the DC area, which is where my personal history in geothermal starts. So I was there. I was a fellow, where among others, I met Joe Rollin, who's on this call, and Olia, who's a good friend, and it was there that I got to help out building funding programs for a variety of high risk, high reward geothermal R&D projects. We'll come back to these in a bit. The agency is much more wide ranging than just geothermal. It was a crash course in everything under the sun and energy. And I really enjoyed the time. Highly recommend it if anybody has the chance to work there. From there, I went to Prime Impact Fund, as I mentioned. I joined there a little over 2 years ago. And as I mentioned, we recently transitioned to its successor fund, which is called Azolla Ventures. Notably absent from all of this is any geothermal operating experience. I do not think of myself as a geothermal expert. I think of myself as more of a super fan. And so I can give overviews and what I think is really exciting about a variety of topics. And I've spent time talking with, every expert who would, pick up the phone and talk to me, but, we should go in clear-eyed that, like, I have never worked at a geothermal plant. I've been to one, and I stupidly did not include the photo of it in this talk, although I have a bunch of other photos. All right. So we'll start from the basics. What is geothermal energy? And again, please stop me if you have any questions along the way. So how it works is you basically need three ingredients. You need heat in the subsurface. You need permeability. So in other words, pathways for fluid to flow in the subsurface. And then you need a fluid. Most often that's water, but it doesn't have to be. How do you harvest it? First, you inject cold fluid into a hot geologic formation. And on this chart here, that's here in the blue, you're injecting cold fluid down. You then let it percolate through a network of cracks, and then you produce the fluid, now heated, back at the surface. And then you run that hot fluid through a power cycle, most commonly some sort of turbine, but it doesn't have to be that either. But you generate power with that. And then you may also do things like running it through a condenser or a bottoming cycle to produce more power from that same fluid. And then you go back to step one, re-injecting it. And so it's this closed loop system that produces power without emitting any carbon. All right. And one thing I'll also note, you'll see here at the bottom left, I'm citing this study called GeoVision. This is sort of the Bible of geothermal. It was produced by the Department of Energy 2 years ago. Really, really fascinating document. It's a great place to start if you're ever interested in geothermal technology. Okay, so there's a bunch of ways you can imagine producing geothermal energy. I think of it as there's 5-ish types. And in reality, the lines kind of blur between a bunch of these. So we'll start with one, which is called a ground source heat pump. And we have an image of this over here. This is home geothermal typically, where it's very shallow. You're simply using the constant temperature a couple feet under the surface of the earth to either heat or cool your home. It's just a constant thermal source that you can use. We won't talk a whole lot about number one, but it's important to note, and there are some really exciting developments happening in that category. Two is called hydrothermal, where you have all three of those elements I mentioned before all in one place. You have water in the subsurface, you have permeability or naturally occurring cracks, and then you have heat relatively near the surface, most commonly on the order of a mile below the surface. All of today's geothermal plants, there may be exceptions now, but pretty much all of them are hydrothermal plants. Third, you have enhanced geothermal systems, also known as EGS, where it's hot, dry rock. You have the heat under the surface, but you have to bring your own water and you have to make your own fractures. And so that's shown here on number 3. One possible way you might envision this. It's typically deeper, it's typically hotter, and it's as we'll get to, it's one of these more emerging topics. Number 4 and 5, which are not shown here, are deep direct use. So producing the heat, but not using it for electricity. You could use it directly from anything for space heating to industrial process heat. And then closed loop geothermal, which is also not shown, where you don't rely on any fractures in the rock at all. Instead, you drill out your entire heat exchanger and not worry about the variability of subsurface fractures. All right. Okay, so who produces it today? There is a relatively short list of countries that produce significant geothermal energy. The US is the top producer, but if you look at the y-axis, it's not all that much power. The US is about 2.5 gigawatts of geothermal electricity. That's tiny compared to the overall power consumption of the country. That's tiny even compared to like how much solar is deployed in a year. The other thing you might notice from this list is where the countries are. They're typically the Pacific nations, all around the Ring of Fire. Geothermal uses subsurface heat. It may make sense for that to be located in seismically active areas where heat can come closer to the surface. So it's typically the Ring of Fire countries plus a few others that have volcanic activity like Iceland. Okay, speaking of Iceland, this is a photo of one of the larger geothermal power plants on the island. We'll show a handful of these throughout, but they do make for really scenic photos. All right, so why bother with geothermal? The big reason, or there's a bunch of big reasons, but one of the first ones that comes to mind is that it's always on. Solar and wind come and go, and as we continue adopting more of it, I think most of us here will know well the challenges that brings. It's a variable source, and either you need to store a lot of it in the form of battery storage or something else, or your grid's going to be very unstable, and that can't happen. So this is a almost live look at California. It was a couple of days ago, where you see the solar curve peaking at about 11 megawatts and then completely disappearing when the sun goes down. You see wind here in blue, kind of coming and going. It's a bit less predictable, but we do have tools to model the wind output. And then you have geothermal in brown, which is just really constant at about a gigawatt. And so it's this rare type of renewable that is also a baseload resource. But it's not just that it's baseload. It is also flexible in principle. It can be sped up, or it can be ramped up or ramped down based on how much water you're pumping through the system. You just turn up or turn down the faucet, essentially. And one compelling way I've seen this shown is from a recent announcement by Google and Fervo Energy, which is a geothermal startup. So here you have their data center energy usage. It's pretty much uniform. They overlay it with variable renewable energy. It comes and goes, leading to these troughs where there may be a gap. And so if you add geothermal and it's a baseload source, it makes the troughs a little bit shallower, but doesn't erase them. But then if you ramp that power up and down, it can completely eliminate them and lead you to 24/7 zero carbon power, which is, again, pretty rare in the world of renewables, and can solve this increasing problem of nighttime hours actually not being decarbonized and getting more and more carbon intense as natural gas fills those voids. And so, I found this visual very useful and compelling. It came off of the heels of an announcement that Fervo Energy will be doing a 5 megawatt geothermal power plant alongside Google. So really exciting stuff. All right. One other, I heard somebody mention in their introduction land use, and this is one of those things that it doesn't get a lot of airtime, even within this small field of geothermal, but it has the smallest land footprint of any renewable, at least I'm aware of. It would be interesting to see the nuclear comparison. I don't know how that lines up, but it's certainly more energy dense in terms of land footprint than wind or PV or legacy power. And so, all right. We've talked about some of the benefits of the resource, but we haven't talked about the absolute magnitude of the resource. The magnitude is massive. And so here we have a couple comparisons where we're talking about proved resources of oil, gas, coal, and uranium. That has a specific economic meaning, proved reserves at a certain market price. These numbers come and go, they fluctuate. But the overall point is that the geothermal resource is orders of magnitude larger than these really, really massive resources that we already know and we already produce today. And this is set against a background where US yearly energy use is about 100 exajoules. We have about 200,000 extractable from geothermal.
Michael, quick question about that. Is that assuming like a certain depth, like extractable? Does that mean like within 5 miles of the surface or something like that?
The next slide will get to that in a bit more detail. I didn't make the 200,000 number. I would have to go back a little bit further. But yeah, so one thing I will say about, some like what has been practical so far is it doesn't line up with that number at all. So on the left side here, the pink dots represent actual geothermal power plants. There are not many. They're mostly in the West, in California, Nevada, and so on. We'll come back to this in a bit, but we've basically been picking the low-hanging fruit.
Mm-hmm. Sounds good. And Tarun, I think that answers your question as well, right? Mm-hmm. Sorry, there was a question in the chat.
Okay. So yeah, there we go. I'll show this explicitly on the next slide too. So the real prize is deeper underground, just in terms of sheer, absolute energy you could produce. So these three graphs, these three maps on the left are from Southern Methodist University, that produces these geothermal maps of the US. As the colors get more purple, that's hotter resources. And again, it's concentrated in the West, but if you go deep enough, it can be anywhere. And so, today's on the right here. So as I mentioned, all plants so far are hydrothermal. And again, we're just focusing on the US right now, but the identified hydrothermal sites are about 6 gigawatts electric. There may be a couple dozen more of undiscovered. But then when you get all the way down to EGS, which is again, you just drill down, you bring your own water, you make your own fractures. That is the really, really massive resource. Okay, so like I said, we've been picking the low-hanging fruit so far. In the US, California has about 3/4 of all the geothermal power. Nevada is about second, and everybody else is in the long tail. Okay, so importantly, that this doesn't cover the many other countries that have strong geothermal resources. I haven't looked at this super closely really recently, but in my experience, it's just been harder to readily find that data. All right, so this brings up the question of why we have been sticking with the low-hanging fruit for so long. We've been doing geothermal for decades, but it's just been this fledgling industry for a while. What's hard about it? So here we have another Icelandic power plant in the photo, and we're going to blow this up here in a second. So if we take a closer look, I want to get across the point that there's a lot that goes into a geothermal plant. I think even above and beyond many other types of plants. And so if we just dissect this photo, you have the power plant and the control center, the center that makes everything run. There's above ground infrastructure, tons of pipes that go from power plant to injection well to production well. You have power lines. Most often these are in pretty remote places. And in order to get the electricity somewhere useful, you have to do one of the hardest things in all of energy, which is build power lines. Nobody wants them near them. There's obviously below ground infrastructure too. That's where I think the most exciting technological advancements are. It's not pictured here for obvious reasons, but there's a ton of that. There's also emissions. It's mostly steam, but every now and then there may be an organic working fluid or something that does get emitted and has to be permitted appropriately. And like I mentioned, these are pretty remote. They generally have to be far away from population centers for both resource and permitting and societal reasons. But there's a lot that goes into this, and that shows up in some of the figures that we'll go through and some of the results in terms of the industry's culture. All right. So I've been drawing this analogy with oil and gas. It's close, but it's definitely not one-to-one. So I'll highlight a couple of key ones here. The bolded one is that per barrel of stuff produced, geothermal is much, much less valuable. Oil right now, I just looked today and it's $80 a barrel. Geothermal is like 25, maybe 50 cents a barrel if you're lucky. And so it means you have to produce a lot more fluid in order to generate a valuable return. Oil can be shipped, stored, transported, sold easily. Geothermal electricity has to be sold locally into a grid. or used at a project that it's powering, or what have you, or directly used to heat a building or something like that. The geology is pretty different. Oil and gas, relatively speaking, those rocks are easier to survey, are generally more regular, whereas geothermal settings are typically either volcanically active or highly fractured, or just plain featureless, which makes it hard to know what's underground before you drill down there. And that adds to risk. The temperatures are really different. Oil and gas, we have plenty of oil and gas without having to go above about 175 C. Whereas geothermal, that's where stuff starts getting good. So they're generally above 175, sometimes above even 250. And that has big implications for what you put down into the ground. For example, electronics that are on a drill bit, some of those stop working above 150 or 175 C, and you have to now re-engineer those systems with one hand tied behind your back because let's say you can't use silicon anymore. I find that challenge interesting, but it is a big challenge. There are others as well. I would just point to the last one here about reservoir depletion. The lifetime of an oil well is typically shorter than a geothermal well. Oil wells have these well-known decline curves that, if you're lucky, you make your money back in 18 months or so, whereas a geothermal well must continuously operate and continuously manage the resource so it doesn't accidentally draw down too much heat and not be able to produce for enough to make a good return. Okay. So we'll next talk about the risks. And the big point I want to get across is that the risk in geothermal development is concentrated when you have to put a hole in the ground, when you have to actually drill earth. And it's for two reasons. One is because you still don't know a whole lot about what's under the surface. Typically, we're getting better at that, but it's just fundamentally hard to know a whole lot before you are down there. And that's also where the cost starts ticking up, and more than ticking up. You're now talking about millions of dollars, maybe tens of millions, rather than hundreds of thousands to single-digit millions. And so this is where the rubber meets the road, quite literally, putting a hole in the ground. To look at this another way, there are, I think the biggest opportunities are in reducing the risk and the cost during resource development. And so a resource goes through a bunch of different stages, all the way from prospect to construction to operation. And getting from one stage to another has pretty different risk profiles, costs of capital, and actual capital intensity. I know there's a lot of text. I don't mean to just make you read all of it. I want to highlight two things. The opportunities I see are to increase where there are low success rates, increase the success rate. So discovery, resource development, and reservoir creation, or reduce the amount of capital it takes to get from one stage to the next. So increase that, reduce that. A lot of ways you can imagine doing that, but that's, I think, where the opportunity is. All right. So I want to take a moment to talk about earthquakes. We are talking here about moving large amounts of water through seismically active areas, and that has the potential to cause earthquakes if it's not done in a responsible way. This term is called induced seismicity, which I think maybe sounds a little less scary. Sometimes it maybe sounds a little more scary, but basically in the mid to late 2000s, this happened a couple of times at geothermal projects. They were not, major earthquakes, they were not like magnitude 7 or 8 earthquakes or anything like that. But they were on the order of like a magnitude 3 earthquake. It's enough to feel, and they were relatively close to the surface. And so they're felt more strongly. And I see somebody in the chat mentioning earthquakes in Oklahoma. So that's actually what I'm showing here on the left, on the bottom left. The oil and gas industry also causes a fair number of earthquakes. This is a screenshot of an app that I have on my phone called My Radar. Among many other things, it can do like weather and wind and whatnot, but it also shows earthquakes. And so this stuff over here, these small earthquakes on the West Coast happen all the time. that's very seismically active. But then if you look at Kansas and Oklahoma, like that doesn't make any sense. Like there aren't faults there. That's typically related to oil and gas wastewater disposal wells. And that's been reported on pretty extensively by environmental reporters. And so it's possible. It has happened. I think generally the industry is pretty, aware of not doing it. Like these stories in the 2009-ish timeframe, they definitely sent ripples through the geothermal industry. But yeah, it's possible that this happens. And so this all begs the question of how does a geothermal project get built? The answer is pretty slowly. The regulatory side is actually pretty tight. It's more tightly regulated than oil and gas, which was a surprise to me. And so in the US, there's the National Environmental Policy Act, it's called, or NEPA. And the oil and gas industry typically gets categorical exclusions from NEPA when developing an oil resource. And so geothermal does not get those today. There's talk in policy circles about making that happen. I'm actually not sure exactly where that stands, but the difference in any case is large. If you get a categorical exclusion, your process for permitting is 2 months-ish versus 2 years if you have to go through the full NEPA process. That really matters when you're trying to finance and build a project. And then on top of that, the people regulating the geothermal industry are typically, they rarely field geothermal permits. They generally aren't expert and often don't prioritize them. And I know Tim Latimer, the CEO of Fervo Energy, has talked about this sort of thing publicly, about how his permit applications have been stuck in review for upwards of a year. Okay, again, if you want to go deeper on this, first place I would go is GeoVision. It's a really fantastic resource. Okay, so let's go next to, there's a couple glimmers of hope on this front. One is that the DOE estimates that regulatory processes that are not better than oil and gases, but just more like them, could cut these development times in half. That's a big deal. So for hydrothermal, it takes an 8-year process to a 4-year process. For EGS, it's more like 10 to 5. There is potential and sort of early signs of bipartisan political support, but it's nobody's #1 priority. Broadly speaking, Democrats like clean energy, Republicans like jobs and oil and gas tech transfer. As I showed before, often geothermal development is in the Mountain West, some red, some purple states. And so there's the basis of potential agreement. The Senate held its first hearing on geothermal 2 years ago, following the publication of GeoVision. I was still at ARPA-E in DC at that point. I had the chance to go and sit there in person. And I would just point out as well that the ClearPath Foundation has been a thought leader on geothermal policy. I've showed some of their graphics earlier, but they're doing good work. Some other levers, state procurement could be a lever to accelerate deployment. California has recently led the way. I'm not expert on the details, but I understand there was a big call for gigawatts more of geothermal. And then I know we have at least one person who mentioned Kenya in their introductions. Kenya is a model country when it comes to geothermal policy and development. Some others are Iceland and New Zealand. Generally these seismically active countries that have large resources that are already either developing or well developed. Okay. So let's move on to why there's never been a time, in my opinion, never been a better time to be a geothermal entrepreneur. And here we're back in the US with this photo. This is a power plant, a smaller power plant in Fallon, Nevada. So in short, I think the reason it's never been a better time is because the world has evolved around us since the 2009 timeframe when things went sideways. First, there's a bunch of tech transfer opportunities. I'll go into a couple of these in the next coming slides, but oil and gas is a big tech transfer opportunity, but it doesn't end there. There are sensing technologies and computational technologies, things like machine learning that can be really applied to these enormous geophysical data sets. We could even draw inspiration from things like space exploration or nuclear or aerospace industries, with the thought that if we are able to make a rover that can survive in the atmosphere of Venus, which is sulfuric acid and extreme temperature swings, maybe we could use some of those same tools and electronics to survive deep underground. There are other factors that are very important. Talent migration is a big one. I've heard from geothermal entrepreneurs about this generally, folks who maybe in the last oil downturn got laid off and were looking for something they could use their skill set to do. There are opportunities, as I mentioned before in the Google Fervo example, there are opportunities to command a premium by doing what solar and wind can't. If you're able to decarbonize nighttime hours and your only competitor is a natural gas peaker plant, let's say, you can charge a higher amount for that electricity at market rates. There are new sources of capital, which I'll touch on at the end. And last but certainly not least, there's a growing buzz around this industry. And I think it's encapsulated by no person better than this woman on screen, Jamie Beard. I met her about 3 years ago at a small workshop. We've stayed in touch since. And over those 3 years, she has founded the Geothermal Entrepreneurship Organization at the University of Texas, Austin. Organized this one of the largest geothermal conferences called Pivot. It's typically every July. Thousands of people attend this. It's been virtual the last 2 years, but and more recently she gave a TED talk all about geothermal and is just generally this force of nature propelling the industry forward with an oil and gas mindset. All right. So given this oil and gas background and tech transfer opportunity, I don't think about this that often, but it's important to know that the US is actually the world's fossil fuel superpower still. These numbers are a couple years old. I checked recently. This trend holds basically, where we produce more oil than Saudi Arabia, more natural gas than Russia, and the GDP of the oil and gas industry equals that of South Korea, the entire country. So this is a massive industry with a lot to be drawn from. And when it comes to enabling technologies, one thing I would look at is essentially the unconventional oil and gas revolution that happened, within the last 10 years, where we started off, up until then, most oil production was what was shown on the left, conventional production. The crude analogy is you stick a straw into the ground and draw oil up. We started transitioning to unconventional, which is more, you find a shale seam that has oil in it, you drill through that layer horizontally, and then you break it up, you frack it to release the oil. The other analogy I like, I basically use every chance I get to show this, is the old way of drilling versus the new way of drilling. Old way is like a jelly donut. The new way is more like tiramisu. Okay, so I'm going to next go through a couple of really exciting areas in geothermal technology that are up and coming to various stages. One, I've mentioned this a couple of times now, enhanced geothermal systems, where the reason you might do this is because, as I showed before, hydrothermal resources are limited. And so if you can bring your own water and create your own permeability, you're in business. This is harder to do in geothermal systems than in oil and gas. And so especially breaking rock in the direction you want it. And so the key player driving this forward, there's two key players that I would highlight. One is the DOE Geothermal Office. They are responsible for the bulk of the R&D funding here in the US. And two things I would highlight is one, the Forge project. This is a site in Utah funded to the tune of about $140 million over 5 years to develop EGS. The other thing I would mention is about 3/4 of that office's budget goes to EGS R&D. And so that is the major source of funding for the US. Anytime there's a big geothermal conference, the director of the GTO is always one of the headliners. They're the center of gravity. The other key player I've mentioned a couple times, Fervo Energy. Their core innovations are horizontal drilling and distributed fiber optic sensing to dramatically increase the productivity and lifetime of geothermal wells. They recently raised a Series B led by Capricorn Investment Group. And like I mentioned, have this project with Google. They seem to be off for the races.
Hey, Michael, quick clarification on that one, if you don't mind. So with Fervo Energy, could you speak a little bit more as to, I'm assuming that the horizontal drilling is useful because some part loses heat over time, or like, could you tell us why the horizontal drilling is important?
Yeah, so it allows you, just broadly, it allows you to build, I don't know what you would call this exactly. This is a heel to toe configuration in the oil and gas world, where you can drill two wells that are close enough to each other that you get a large heat exchange surface and a minimal travel distance between the two wells, your producer and your injector. There's a lot of other ways you could imagine building that same sort of like close network of wells. You'd have to talk to an actual subsurface engineer to go deeper into it than that. But I think about, at least in oil, like horizontal drilling was an enabler. It wasn't the end all be all in its own right, but it enabled people to do hydraulic fracturing and accessing these shale seams more effectively. And so, I think that's where I would go there. The other thing I'd mention about Fervo is it's, if you talk to or listen to Tim, the CEO, he paints a more continuous picture between conventional and EGS. There's a continuum between EGS and non. And I think they play at that intersection.
Awesome. And Korea, I think you had a question in the chat.
Yes, I did. Essentially, I don't know much about geology or subsurface engineering, though I'm a mechanical engineer anyway. But essentially, a geothermal expert that I spoke to once told me that, at least in the Kenya case, he told me that there is this risk of, and it's already been seen, where the actual power production is lower than what was estimated at the time of development. And so if you want to expand into like to produce more, perhaps it presents this risk that it's not going to meet the supply is not going to meet the demand of the future. So I was just wondering what you know about that.
Yeah, it's a great point. Like that has happened plenty of times. All the way from completely dry holes, as they say, like there's no resource where you thought there was, to just an underperforming resource. Like that happens. And I'm going to go back to some of the maps I showed before. Like we have these national level resource assessments, and that's all well and good, but when you get down to it, you have to know something much more intricate and local level. And if you talk to geothermal startups, doing exploration, I'll get to the company that we know the best. But this stuff can vary even at the like tens of meters level. You measure over here, you say, I'm going to drill a well over here. It's not, the resource isn't exactly what you thought it was, because maybe this upwelling in heat was tens of meters that way accidentally, or not accidentally, but you just didn't have the tools to measure it at the time. And so the upside there is that you can, if you start to nail that through new technologies, and seismic is a good example, advanced seismic is a good example of that. You can avoid this underperformance problem and make it from an exploration process into something closer to a manufacturing process where you know the quality of the resource better. But there is just inherent resource risk, and that gets factored into things like the capital you would allocate to a project. Today it's something like 20% of wells are successful, and so just roughly, you'd have to budget about 5 times as much money as you would to drill one well in order to think you'll be successful. So it's a great point, a valid concern, and that, you know, that does happen.
Yeah, I'm not cynical about it, by the way, just to be on the record, because I've seen for example, unfortunately in oil and gas sector, there've been breakthroughs in subsea production because of technology. So I think there's potential in geothermal.
Yeah. Okay. The next technology I find pretty interesting is closed loop, where, as I mentioned before, the idea is don't bother with fractures in the subsurface at all. Just drill from point A to point B. And the complication here is that drilling is really expensive. And in terms of heat exchange, tubes are worse than fractures. There's lower surface area per unit water. There's lower heat exchange surface area. There are a couple companies going after this. Ever Technologies being one. This graphic on the bottom right is from them, where they've essentially drilled a capillary network from one set of wells to another. There are other permutations on this design, such as single wellbore designs, or these sorts of hybrid closed loop plus convective heat transfer systems. This is an area people are starting to explore more aggressively. The reason I have a potato press on the top right is from a professor named Eric Van Oort at UT Austin, who's a former Shell driller, who once told about this idea, said, why wouldn't you just drill something like a potato press? And so you can get creative with how you do this. The question is just, can you harvest enough heat economically to make it work? The risk is lower in that you can drill where you want, but it's going to be expensive to do. And so either you want to go shallower or find some other way around that. All right. So the last specific one I want to go through is predictive exploration, and, you know, cards on the table here. We have a bet in this category through Prime Impact Fund. So the problem statement, so to speak, is that many geothermal resources are blind. There's no way to tell that they're there from the surface. The solution to this would be to apply more modern techniques, ranging from statistical techniques like machine learning to more advanced seismic surveys in order to identify and de-risk likely resources. There's a lot that can be drawn from oil and gas surveying, although, as I mentioned, it's generally harder to do in geothermal, and you're looking for different sets of signals. And as a result, you know, data sets in this field are often limited or expensive to build from in your own right. It's hard to get a ground truth without a bunch of capital behind it. So our bet is on a company called Zanskar. They're based in the Salt Lake City area, where they have developed a set of advanced analytics and subsurface imaging tools in order to, as I hinted before, turn this sort of bespoke and uncertain process into something that is predictable and scalable. All right. So there's a lot of other interesting ideas out there. I'm not going to go through all of these, but just to highlight one or two, there are novel drilling physics that a couple of people around the country and world are working on. Today's drill bits are, they're physical bits that mechanically scrape away rock in a circular motion, but it doesn't have to be that way. There's a lot of ways to break rock. One of those is by melting or vaporizing it with concentrated beams of millimeter waves. Back at ARPA-E, we funded one such project that has led to the development of a startup called Quaise Energy, where that is what they're doing. They're trying to build bigger and bigger millimeter wave beam forming drill rigs, essentially, to melt and blast away rock. Another that we funded at ARPA-E was for this downhole fiber optic sensing tool set, where Fervo Energy was one of the recipients, along with another company called Class 6 Solutions, where essentially what you're looking at in orange are these surface orbital vibrators. They spin really fast and generate this low intensity seismic wave. And what's not pictured here is that this would be in proximity to a geothermal well with a fiber optic sensor installed in it. And so your fiber optic receives the signal that's generated at the surface, and you can use the reflections of those waves to tell useful features about what is going on in your operating geothermal well. And so, one of the things, just stepping back for a second, one of the things that drew me to this field in the first place is that there's a really big technical sandbox you can play in. Everything from mechanical to optical to chemical, biological even. There's a lot of different things you can draw on to make progress in this field. The other thing I meant to mention this up front, but as I started going to geothermal conferences, I noticed a lot of people were not trained as geothermal engineers or even geologists. Chemical engineers, mechanical engineers, electrical engineers were all at these conferences, and it's one of these fields that not that many people come up in from the very beginning. A lot of people come to later on. Okay. Last, I want to talk just a bit about capital. And back in ancient history, i.e. 5 to 10 years ago, there was very little capital out there, venture capital specifically for geothermal. This pie chart is from Brookings from a couple of years ago, where at the time, clean tech VC, as it was called then, was about $5 billion a year. The fraction going to geothermal was less than 1%. And if you just multiply the two, that's like $20 million of geothermal investment per year of any kind. Today, it's a very different picture. So at the climate tech level, in the first half of this year alone, there's $16 billion invested across about 250 different investments. And just from looking at 3 or 4 companies' Crunchbase pages, here's an incomplete list of investors who have invested in geothermal just in the last 2 years. There's dozens. There are many others that are not captured here, especially among oil and gas venture arms. There are 2 here, BP and Chevron, but there are many others that have gotten involved. And so that's one thing that's changed. That's another reason it's a really exciting time to be in geothermal. All right. That's all the content. Just to sum things up, my journey to geothermal has been unusual, but so is everybody else's as I got to know the field. Second, geothermal is an underutilized resource that I think could power. Well, we know it could power the planet many times over. I think we could do a lot more with it than we currently are. Third, producing geothermal is similar to, but generally harder than producing oil and gas. And it's never been a better time to be in this field as an entrepreneur, because there's new technologies to use, there's new talent to draw from, there's new opportunities to create value based on what time of day it is or where you are. There's new sources of capital, and there's new buzz in the field. And so I think all of that adds up to a really exciting picture. I will stop there and thank everybody for joining me again on a Sunday. Really appreciate it. And just to make a quick plug, I've started to write at the URL down below about topics like this, but more generally about climate technology and adaptation. So I'll stop there. Thanks, everybody.
Thanks, Michael. All right, everybody, please unmute yourselves and clap vigorously.
Way.
Awesome. Thank you for this amazing overview. If anybody's got questions, please raise your hand. So I go to the participant and click on the raise hand button, and I will call on you based on the order that appears for me. So Philip, go ahead.
Yeah, thanks for a super interesting talk. I have a bunch of questions, but I think the first one that sort of springs to mind to me is, you kind of repeated the potential quite a bit and how much it could solve our energy demand. And what's a little unclear to me is how concentrated that is in the regions that you kind of identified, like the Pacific countries, the Ring of Fire, places with seismic activity. Iceland obviously also has like a huge potential, but like, for instance, to really provide like a really good base load in, say, a Nordic country in Europe, or in, say, I don't know, the middle of Russia or something, would that, what sort of what sort of potential is there, and does it depend on some of these more sort of trickier technologies like EGS that you were talking about?
The short answer is yeah, it totally does. I'll show some bigger versions of the maps from earlier. The takeaway is you would probably, just given how things evolve, going from 3.5 to 4.5 to 7.5 to 10 kilometers, like you would rationally build out more geothermal in the West way before you would start dealing with like Florida. And so generally speaking, there aren't hydrothermal resources, outside these seismically active areas. And so, yeah, you would be relying on the development of EGS. I would describe that as more of, a long-term moonshot than something that is going to happen in the next, couple of years. But the potential is there if you make, essentially, if you make drilling and fracturing cheap enough that it can be done, really economically in the West, but also economically in the East. One other idea I've found intriguing, but I'm a bit skeptical of personally, is the idea of, for example, in like West Virginia, drilling geothermal underneath an existing coal power plant, and then using the surface equipment from the coal plant to just deal with geothermal steam instead of coal-fired steam. And you'd have to retrofit quite a bit, I'm sure, but you could save on the surface equipment at least. That's an idea that's been out there. I don't know where it stands today, but
you have the transmission lines already anyway.
Yeah.
Yeah. Okay,
yeah.
Thank you. Yeah.
And it feels like you could do that with natural gas in the West as well. Daisy, go ahead.
Hello. So I was wondering, you said that geothermal could like power the world many times over, but also it's not something you can transport. I've seen maps of the potential of things like offshore wind related, like relative to the energy demand of the geographies that they're nearby. Do you have anything like that for geothermal to kind of show like what proportion of humanity lives within a reasonable transmission distance of the energy from geothermal? I'd be really interested to see that if so.
I don't, but I wish I did. That is the question, right? Like you've homed in on it perfectly. Just looking at this map, so much of the resources in the Mountain West, where it's precisely some of the least populated areas. So yeah, that's a real challenge. If we were to do things like install HVDC grids that go across the country, that could alleviate some of it, but that's its own independent, very hard challenge. So you're right to point that out. That is a big sticking point for this field.
Joe, go ahead.
Thanks, Mike. Really fun overview. You gave that very brief little comment about biological elements. I'd love to hear a little more about that.
Yeah, I'm not sure it will be the most exciting to someone like you, Joe, but one thing you have to do is control biological buildup on your pipes. The oil and gas industry has developed all these pretty horrific biocides. I imagine a lot of those are deployed in geothermal already, but I'm not expert there. Maybe if it's hot enough, it's not a problem. The other sort of interesting thing is, there's what are the two companies? There's one company called Biota, one company called 16S that do biological surveying for oil and gas. You can develop a fingerprint based on where you are in the subsurface that correlates with different types of rock or different locations around the country. And so I could imagine maybe if you're doing sedimentary geothermal, you could draw from that. But yeah, mostly it's, I would not describe that as the biggest piece of the pie.
No, but that's interesting. I had never made the connection before, but an old friend and former co-founder, it like works for Exxon in oil and gas specific microbiology on the kind of things you're describing. So
Yeah.
we'll definitely be pinging him on that topic.
Cool.
Chris?
One of my concerns is that renewable energy is not always clean energy, and that in the case of geothermal, the low-hanging fruit is going to be near hot springs, which in New Zealand, for example, lowered the temperature of those ecosystems and also caused geysers to stop functioning. So I'm interested in this idea that there's a lot more geothermal out there than is, traditionally accessible. Can you talk maybe a little more about how likely it is we're going to be getting to these deeper locations so that we can site the geothermal plants away from delicate ecosystems?
Yeah, very, very thoughtful question. So I think I want to tease apart two things. One is within existing hydrothermal systems, like siting them and managing the reservoirs responsibly. I suspect that would take away a lot of the the adverse side effects. Coming back to the plant that I had visited a couple of years ago, it was in outside of Reno. It's called the Steamboat geothermal plant. Through essentially good management of the plant, that plant has outlived its 30-year expected time horizon by quite a bit, and is they've managed the temperature decline to a point where it's basically beating expectations. So that is possible. You may take a hit up front if you don't produce as much energy as you might want to otherwise, but that seems mostly like an operator decision-making issue. Obviously, if you've misjudged the resource in some way, that could lead you to a harder place. And then the second piece, the dream with EGS is that you could do this almost anywhere, and definitely prioritize being away from population centers or sensitive ecosystems. What we would need to do in order to get there is demonstrate overall drilling processes that are much cheaper than where we're at today. And when I say that, I don't just mean the time the drill bit is active. The process of startup and shutdown and like measuring the temperature every once in a while is also pretty cumbersome. And I think there's a lot of like process and operational improvements that could be done to make that cheaper. And we need some breakthroughs in subsurface engineering. There was one center that's working on this is also funded by the Department of Energy's Geothermal Office. It's called EGS CoLab. It's in South Dakota. And one of the thrusts of that research program is attempting to fracture from point A to point B in this pristine slab of igneous rock, which is just harder than doing so in oil and gas bearing shale. We just don't know as much. We haven't had as many shots on goal as we have in the oil and gas industry. And so, just to be frank, we need breakthroughs there, or some other breakthrough in closed loop that gets rid of the need for fractures entirely. That would seem to be, well, I don't know. It would be a deep spreadsheeting exercise, as well as a definite execution question. Ola, you're muted.
Awesome. Thanks. Sean, go ahead.
Hello, thank you so much for that wonderful talk. I was wondering what you mentioned that the difficulty with the capital intensity of resource exploration, and I was wondering, is that typically funded just purely in corporate equity cash, probably backed up by some of those like aligned equity investors you're talking about? And like how does that typically compare with the capital allocation for resource exploration in like conventional, like high costs, like deep offshore oil exploration?
That's a great question. I'm not going to have a very satisfactory answer. Let's take the case of a relatively low risk geothermal resource. You would do that through project finance, where with a mix of debt and equity, an off-taker signing a PPA, many parties coming together on one deal overall. Project finance is its own, its own whole section of finance that I am not expert in, but I know that is generally speaking how these things get done. If you're a startup, you may do things through corporate equity instead, because it's generally speaking easier to raise early on. I think for some of these emerging companies, it's probably going to be a mix of both. Is there anything else I would add to that? I think I would leave it there, unless I missed some parts of your question.
No, thank you so much. I think I'd just like to clarify that, like, even in the conventional established space, normally resource exploration is done before project finance. That's done on corporate balance book. And then once you find a resource and have done it, then you get your PPAs and then you get your project financing. So that's that pre-project finance part for things that will eventually become projects, which is still, to me, the big sticking point.
Yeah, that picture you painted sounds about right to me.
Yep.
With limited experience in it, but
yeah, we'll talk more.
Yeah,
thank you.
Yeah, please, you should reach out.
Awesome. And one last question, DC.
Hi there. Yeah, I typed it up, but everything you said makes total sense. And there's a lot of energy here. The technology's mostly ready to go. So what's holding it back? Why aren't people that do project finance throwing billions of dollars at building the plants and generating energy?
Maybe I painted too rosy a picture. Some of these emerging technologies are not quite ready to go, and in order to prove them out to the scale where project finance investors would throw billions in, more piloting and more operation, and ideally years of operation of plants will be needed to be shown. What we know works really well is hydrothermal, but you have to really heavy up and allocate a lot more capital than it would take to actually drill the number of wells that will be productive. We're hopeful we can reduce that, but that's basically why not everything is ready to go.
Okay, so what does it take? Is that government funding? Is that ARPA throwing money at it? Is it tax breaks? All the above?
Yeah, not to just give the cop-out answer. I think all of the above, having thought about it a bit. One thing that we couldn't do back at ARPA-E was fund drilling projects, which everybody was clamoring for when we would convene people. Convene people who are working at geothermal companies and national labs and everything. We got that feedback loud and clear, but it just wasn't in the agency's mandate. And so I'm hopeful for things like the ARPA-E scale-up program to put greater than $10 million towards single projects where maybe drilling a new geothermal well could be a part of that, or at least sort of like retrofitting or upgrading existing geothermal wells that were not fully completed or something. But yeah, we need a lot more holes in the ground with real life data coming out of them. Ideally, viable power production. And so, and then besides that, I think venture capital can play a big role. It's starting to again. Ultimately, I would love to see some of these projects get financed by like the DOE loan programs office. But I think we may be a little bit further out from that.
Great, thanks so much. It's a wonderful presentation.
Thank you.
Okay, we're gonna do Eugene and Daisy, and then we're gonna cut off the questions and go to breakout rooms. So Eugene, go ahead.
I just have a couple of comments. One is, well, first of all, thanks for the very interesting talk. There was a brief mention of footprint of nuclear. I would probably include the 30-kilometer exclusion zone in Chernobyl and divide that between all the power stations and also the storage. So I'd probably include those in the footprint. Just a brief comment there. The other one is sort of in jest, but maybe we should call it shale thermal. I think that will get a few of those oil people on board. They'll just, they might get a few more funds.
Yeah, yeah. I mean, quite a bit of geothermal is in sedimentary basins. So that's something people are working on.
Yeah, well, just call it shale thermal. I mean, that
Yeah.
will that will get lots of people on board.
Awesome, Daisy, go ahead.
Hey again. So you mentioned something about the oil and gas exploration being largely funded by the government, or someone had said it was largely funded by project or by the companies. But my understanding is there's an office of oil and gas exploration within USGS, and it's funded quite a lot, and that the government actually funds a lot of the exploration for the oil and gas sector. And then companies like Google and Amazon Web Services, host and create tools for them as well. What kind of lobbying, if any, or interest within the government is there to do some of the exploration on behalf of the industry? Is there any effort to try and get that done? And then also, is there any support from like Google's tools to help with geothermal exploration as well? So like, what's the ecosystem of trying to get more of that exploration done without it having to come from investment from the industry directly? Yes.
Fantastic question. On the lobbying side, I don't know. On developing some of these tools, you're right to point out that government funding has funded tons and tons of oil and gas technology, if not direct exploration. There's a story that somebody else would tell better than me about how DOE funding undergirded the shale revolution. Decades of R&D grants toward shale resource development led to this revolution that we've now seen. So yeah, look, one hope is that the same thing happens for geothermal. And like I mentioned, the geothermal office at DOE has north of $100 million a year. 3/4 of that going to EGS. And is the Forge project being a great example of somebody stepping up and drilling a hole into the ground and letting people do research on that site, whether it's fracking or additional drilling for offshoots or different seismic surveys. There's a lot that I'm hopeful will come out of that site, but yeah, you're right. I'd love to see more, but it's like everything. It's a balance between various demands and government.
Awesome. Thank you so much, Michael. All right, everybody unmute yourself. Let's do one more round of applause. And thank you both for the wonderful talk and for fielding all of the questions.